Warm greetings everyone. Now we are going to see the unit Earthquake Effects on Structures. This unit covers the major topics of inertia force, the effects of architectural features, the load transfer path, the heuristic behavior, the pinching and Bossinger effects, the concepts of energy dissipation, P delta, and the story drift. Then it covers the behavior of masonry and reinforced concrete structures under earthquakes, the typical failures, the causes of damage, and the lessons learned from the past earthquakes. So, upon the topic of inertia force, so we generally know that when earthquake occurs, the ground under the structure begins to vibrate. Since the foundation is in the direct contact with the soil, the foundation moves along with the ground motion. So the mass of the structure above the soil remains in the original state due to inertia. So the forces which are not externally applied, but they generally internally, as the structure resists on the ground acceleration. So to mathematically express the inertia force, that is explained by the Newton's second law of motion, where F is equal to m into A. So here m represents the mass of the component and A represents the ground acceleration during the earthquake. So here the force directly proportional to the mass of a structure. So to illustrate example, we take or we can visualize the concept of inertia. We take a shake table. Okay, so in such kind of test, a scaled building model will be placed on the platform. So as the table moves, the base of the building follows the same ground motion, while the top tries to remain stationary due to inertia. So this creates lateral forces that push and pull the structure. When compared to the response of a real building, the magnitude of inertia depends on the characteristics of a structure. So light structures, example wooden house, will experience small inertia force, whereas structures with very heavy load possess or attract large amount of forces. So the key points that to be understand for inertia are, so the magnitude increases with the mass of the structure and the severity of the ground motion. So while designing a structure and a seismic earthquake or under concepts of seismic design, so it requires a careful compromise. So this image will relevant to the example for the inertia force under ground motion. The next concept is the load transfer path. So in structural engineering, the load transfer path refers to the load which is transferred through some route. Okay. So during an earthquake, inertial forces are generated in the structure's mass, as we discussed in the previous topic. So these forces will find a path that is an uninterrupted path, that is to be transferred to the foundation, and finally it will be transferred to the soil. So a well-defined path will ensure that all the structural components must work together harmoniously to resist the upcoming seismic actions. So the structural elements of the path, which includes that the loads are transferred to the beams which act as horizontal load carrying members. From the beams, the force will be carrying to the columns and shear walls. Then finally it will deliver to the foundation, which will turn pass to the soil. So here the continuity plays an important role, where if the load path is interrupted, for example by weak connections, that is between the beams and columns, the earthquake forces cannot be transmitted efficiently. Instead, the stress concentrations will build up internally, which lead to the brittle failure. Similarly, the irregularities or discontinuities, such as the sudden changes in the stiffness, will create points of weakness that will likely to initiate the failure of the structure. So the common problems that are related to the load path are, first one, the floating columns. So the floating column indicates that the columns which rest on beams instead of foundations. Okay, so these create the discontinuities because they completely rely on other structural members for the load transfer. Then the second one is the open ground story, such as soft story buildings, which includes the parking levels that without infill walls. And another example, then the large cantilever projections and soft storage will also result in the poor load distribution. So the difference between the good and the poor load path can be illustrated with some examples. So in well-designed buildings, so the load flows smoothly from slab to the beams, beam to the columns, and columns to foundation without any changes or weak connection. This kind of load transfer path is a good transfer path. In contrast, so poorly designed buildings show irregular layouts, discontinuities, unsupported members, so they create the vulnerable points. So the next topic is the effect of architectural features on behavior of structures. So we know that architecture plays a vital role in determining how a structure responds to an earthquake. While the structural engineers focus on strength and stability, whereas the architects focus on the shape, layout, and the overall form of the building. These choices can either enhance or severely weaken the seismic performance. So a building that is symmetrical, simple, and uniform tends to perform well because earthquake forces are distributed evenly. On the other hand, irregular shapes, discontinuities, or poor arrangements can cause concentration of forces, torsional effects, and weak zones, which leads to the premature failures. So one of the main factors is the plan irregularities. So buildings with irregular floor plans are more vulnerable during earthquakes compared to with those having irregular or rectangular shaped buildings. Okay, the L-shaped buildings, T-shaped buildings, U-shaped buildings. So these kind of plans tends to concentrate the stresses at the re-entrant corners where the cracks and the separations often initiate during earthquakes. The next concept is the vertical irregularity. So these are another major source of seismic weakness. That is the buildings with sudden changes in height, such as setbacks or floating stories. So they experience uneven distribution of lateral forces. So the soft stories are often found in ground level parking or for the commercial spaces. They especially very dangerous because they attract large deformations when compared to the upper levels. So that will directly lead to the collapse of the structure. That is the mass and stiffness irregularity. So another critical factor, that the uneven distribution of mass and stiffness, which leads to the failure. So heavy element structures such as water tanks, heavy roofs or equipments. So here the major weight is concentrated at certain levels. They attract large seismic force that increases the risk of local failures. Similarly, placing walls or structural elements unevenly leads to stiffness irregularity, where some part of the building resists motion more than the other part of the building. So this results in the uneven drift, torsion, and the localized damage to the structures. So the design recommendations for architects are, so the buildings with symmetrical plans, uniform vertical profiles, and unevenly distributed mass and stiffness, they consistently perform better in seismic conditions. So the architect should avoid re-entrant corners, floating columns, large cantilevers, and soft stories wherever it is possible. So when functional requirements demand such features, engineers must be consulted for proper strengthening measures. Ultimately, good seismic design is not just about strength, but also it should avoid weakness, and much of that depends on the thoughtful architectural planning. So the next topic is the historistic behavior of reinforced concrete, steel, and the pre-stressed concrete structures. So we know that the earthquake imposed repeated cycles of loading and unloading on the structures as the ground vibrates back and forth. So unlike static loads which act on direction, seismic forces reverse continuously. This causes structures members to undergo cyclic tension compression, leading to unique stress strain behavior not seen under normal service loads. The ability of a material or structural system to withstand these cycles without significant strength, degradation, or brittle failure is termed as hysteretic behavior. When a structural element is subjected to cyclic loading, the load deformation curve does not retrace the same path during loading and reloading. Instead, a loop will be formed in a graph. So that loop is called as the hysteresis loop. So the area enclosed by the hysteresis loop represents the amount of energy that is dissipated during one cycle. So the reinforced concrete structures dissipate energy through cracking of concrete and the yielding of reinforcement, whereas the steel structures show stable hysteresis loop due to the plastic hinging, where the pre-stressed concrete tends to show more stiffness initially but may degrade faster. The pinching effect. So this is a common phenomenon in reinforced concrete where the hysteresis loop becomes a narrow near the origin in successive cycles. This effect is called as pinching effect. So here the energy dissipation capacity reduces with repeated shaking, making the structure more vulnerable. So pinching is particularly pronounced in poorly detailed members, in filled frame systems, elements with low confinement. Engineers must recognize this limitation and provide adequate detailing to ensure sufficient ductility. So the in steel members, cyclic loading reveals another phenomenon called the Basinger effect. When a steel element is first loaded beyond its yield strength in one direction and then reloaded in the opposite direction, the yield strength reduces in the reverse direction. So this occurs due to internal changes in the steel's microstructure. As a result, the material yields earlier under reverse loading, making it less capable of sustaining repeated cycles. So this effect is a significant factor in seismic design as it explains why even ductile steel may show strength reduction after several cycles of strong shaking. The engineering significance of this behavior determines how much the earthquake energy a structure can absorb before failing. RCC relies on ductility of reinforcement and confinement of concrete. Steel benefits from its plastic deformation capacity, whereas pre-stressed concrete requires careful design to avoid brittle failures. Recognizing effects like pinching and Basinger effect, it helps the engineers design for adequate energy dissipation. The modern seismic codes emphasize the ductile detailing, confinement reinforcement, and the capacity design principles precisely to ensure the favorable hysteretic performance. Ultimately, hysteresis is at the heart of earthquake-resistant design philosophy. The next concept is the energy dissipation. So when earthquake strikes, the structure will be subjected to a sudden inflow of dynamic energy from the ground shaking. This energy can be either absorbed or stored temporarily or dissipated by the structure. The total input energy distributed into the elastic strain energy, which is recoverable inelastic energy due to material yielding, and energy lost through damping mechanisms. So the energy dissipation is a fundamental mechanism by which buildings survive earthquakes without total failure. So the steel structures are highly efficient in energy dissipation due to their ability to undergo large plastic deformations without significant strength loss. The plastic hinges that form in beams and the braces absorb energy cycle after cycle, providing resilience. Pre-stressed concrete, on the other hand, is stiffer and more elastic, meaning it stores more energy but less energy dissipation. This makes the pre-stressed structures vulnerable to sudden failures if not designed with additional ductility measures. In addition to the inherent material behavior, engineers often incorporate special devices to improve these structures' energy dissipation. Examples which includes the viscose dampers that absorbs the energy through fluid motion, then the friction dampers which use the sliding surface to dissipate energy, and the yielding dampers which absorb energy through controlled plastic deformations. The base isolation system is also another effective approach where energy is dissipated at the foundation level itself, which reduces the demands on the superstructure. So these kind of technologies have been successfully implemented in bridges, hospitals, high-rise buildings, etc. So the past earthquakes have clearly demonstrated the importance of energy dissipation. For example, if we take the Kobe, the earthquake that is occurred in Japan in 1995, so many conventional buildings are heavily damaged. Similarly, structures with the well-detailed ductile frames in California, which has shown the superior performance when compared to such kind of provisions. So these cases highlight that resilience against earthquake does not solely depend on strength, but also on the ability to absorb and dissipate the seismic energy. Designing for ductility and incorporating dissipation mechanisms in a structure is a cornerstone of modern seismic design. The next major effect is the P delta effect. So it is also known as the secondary moment effect. So it's an important phenomenon that is majorly observed in tall or slender structures that are subjected to lateral deformations or displacements. So when an axial load P is applied on a column or a frame, so which undergoes a lateral displacement delta, so an additional moment equal to the product of the load and the displacement, it is induced. This moment increases the bending stress and amplifies the deflections. In the context of earthquakes, where lateral displacements are significant, the P delta effect can destabilize a structure, and if it remains unchecked, it may lead to the progressive collapse of the structure. The mathematical expression is that the P delta can be expressed as P into del. Here the P represents vertical load and the del represents the lateral sway movement that is occurred due to the earthquake forces. So the tall and slender buildings are particularly sensitive to the P delta effect because they experience significant lateral displacement during earthquakes. The additional secondary moments can lead to loss of stiffness and reduction in overall load carrying capacity. In the extreme kind of cases, these effects may trigger a geometric instability known as structural overturning or side sway collapse. Even in the moderate drifts, when combined with high vertical loads, can magnify displacements further, creating a feedback loop that pushes the structure towards instability. The P delta effect has contributed to several building failures that are observed under past earthquakes. So the structures with heavy upper stories or irregular vertical mass distribution systems have shown severe tilting or collapse due to amplified lateral displacements. For example, the soft-story buildings which already experience larger drifts at the ground level are highly vulnerable to P delta effect. Similarly, slender towers or poorly braced high-rise structures have shown instability when subjected to combined vertical and lateral seismic loads. So the engineers can adapt several strategies to mitigate or to control the P delta effect in structures. One of the methods is to increase the lateral stiffness of the building through or by providing the shear walls, based frames or core wall kind of structures, because they reduce the displacement and also varyingly it reduces the secondary moments. The another control measure is to reduce the axial load on slender columns. Then the modern seismic codes mandate the P delta checkings in design calculations, especially for tall structures. Additionally, capacity design principles and the use of high ductility detailing that ensures that even the P delta effect occurs, the structure has sufficient reserve strength and ductility to prevent the catastrophic effect or the collapse of the structure. The next interesting topic is the story drift. Okay, so this is nothing but the relative lateral displacement between the two consecutive floors in a building that is under the action of earthquake forces. In simple terms, it can be easily represented the how much one story of the building moves sideways, that is relative to the below or above the story. So while total building displacement is important, story drift is even more critical because it reflects the deformation demands on individual stories. Excessive drift not only affects the structural integrity of columns, beams and joints, but also damages the non-structural elements such as the infill walls, the glass panels, and the partition structures. So the Dori drift can also be mathematically expressed where the drift is equal to del I minus 1 by h, where del I and del I minus 1 are the displacements of the upper and the lower force respectively. The codal provisions such as the IS 1893, so it prescribes some allowable drift limit that is around 0.004 times the height of the story. So the excessive drift which has the multiple negative consequences. So structurally it leads to a large inelastic demands on columns, beam column joints that may result in cracking, spalling or even shear failure. For non-structural components, the excessive drift causes the partition walls to crack, glazing systems to shatter and facade elements to detach. Additionally, excessive drift magnifies secondary drift like the P delta phenomenon, further destabilizing the structure. Therefore, controlling drift is essential not just for the structural performance but also for the safety and the functionality of the structure during and after the earthquake. So this we have already seen that the codal provisions, that is in IS 1893, the codal the maximum permissible drift is usually 0.004 h. This is for buildings with brittle non-structural components. Even lower limits may apply. Several strategies are used to control the story drift. So the one of the measures is to increase the lateral stiffness by providing the shear walls, braced frames or moment resisting frames, so that will reduce the displacement. The next type of control measure is to build a structure with regular geometry, symmetrical layouts and a uniform distribution of mass and stiffness, so that will prevent the localized drift. In case of high-rise structures, base isolation systems and the energy dissipation devices are very effective in limiting the drift. At last, so drift control is not only a matter of strength but also of ductility and detailing, ensuring that the structures will remain resilient and functional even under the strong seismic shaking. So now going on to the next topic, the behavior of masonry structures under earthquakes. We know that the masonry is nothing but the brick or stone that has been widely used in construction due to its availability, strength in compression and durability. However, the performance of these materials under earthquake loading is very poor because the masonry elements are very brittle in nature and they are very weak in tension and shear. So unlike the reinforced concrete or steel, these masonry materials will lack ductility, so that cannot be absorbed the significant seismic energy. The past earthquake has shown recurring patterns of failure in masonry buildings. The most common failure is the diagonal shear cracking. Then the another type of failure is the out of plane wall failure. So the separation of the corners and junctions is also a common failure, as walls often lack proper interlocking. In stone masonry structures, the bonding and the random rubble construction is poor, so that will worsen the seismic performance, leading to a large scale collapse. The seismic behavior of masonry structures depends on several factors. The quality of mortar plays a crucial role, as weak mortar joints provide little resistance to shear forces. So the wall thickness and the height of the masonry structure also affect the stability, with slender walls being more vulnerable to out of plane collapse. Also, the lack of roof diaphragm action or the poor anchorage between the walls and the roofs further reduces stability during shaking. So to improve the earthquake resistance of masonry structures, some strengthening measures can be incorporated. One is they provide the provision of horizontal bands at the plinth level or lintel level or roof levels that will ensure the integrity by tying the walls together. Another the measure is to provide the vertical reinforcement at corners and junctions, so that will help to resist the in-plane and out-of-plane bonding. The provision of wire mesh or ferrocement overlays can enhance the ductility that will reduce the cracking. While retrofitting the existing buildings with concrete or steel frames, so to confine the masonry walls is also a proven strategy. So the poor performance of masonry buildings has been nearly observed in previous earthquakes such as the Bhuj earthquake, the Nepal earthquake, or the Turkey earthquake, where the thousands of unreinforced masonry houses has been collapsed. So these disasters underline the need for seismic safety measures in the low-rise masonry construction, especially in developing regions. So they emphasize the importance of using confined masonry, seismic bands, and proper bonding techniques. With these provisions, even the traditional masonry can achieve considerable considerable earthquake resistance, protecting the lives of the people and reducing the economic losses. So next, we will see about the behavior of the reinforced concrete structures under past earthquakes. So generally, the reinforced concrete structures, when properly designed and detailed, so they can perform well under earthquake loading because they have adequate strength and the ductility. However, the past earthquake data has been shown that many reinforced concrete structures fail because of poor detailing, irregular layouts, and the lack of compliance with the seismic design codes. Earthquake demand structures to perform and dissipate energy, but brittle associated elements or weak connections, which leads to the premature failure. Some of the typical failures are the soft story collapse, which is most common in the more common where the ground floor have fewer walls or columns, so that will lead to excessive drift and sudden failure. Then the short column effect, that is occurs when columns are partially restrained by infill walls, causing them to crack and shear. The poor beam column joints often fail due to a lack of confinement reinforcement. Additionally, inadequate lap splices, insufficient anchorage, and poor quality concrete have also been observed as major causes of damage in past earthquakes. So some of the case studies like the Bhuj earthquake in 2001. So in this earthquake, it indicates the many multi-storied RCC buildings collapsed due to soft story mechanism and poor detailing. Then due to the Nepal earthquake in 2015, so many non-ductile RCC frames failed, while properly detailed ductile frames, they survived with minor damage. Similarly, in the Turkey Syria earthquake at 2023, so major reinforced concrete buildings crumbled due to irregularity and the lack of seismic detailing, underscoring the importance of the code compliance and the ductile design. So some of the factors that influence seismic performance are the structural configuration, poor detailing of reinforcement, the material quality, presence of non-structural infill walls, and the adherence to seismic design codes and the ductile detailing practices. So when come to the lessons learned and the improvements, so the need for the ductile detailing, that is the provision of the confinement reinforcement in joints, it should be well established. The providing the strong and continuous load transfer path, avoiding the weak story designs, ensuring a proper anchorage reinforcement are essential for maintaining the safety. Modern seismic codes incorporate these kind of lessons, so making the ductile design that should be mandatory while designing an earthquake resistant building, especially in the earthquake prone areas. Ultimately, the resilience of RCC structures depends not just on engineering design but also on strict quality control. So while taking the overview of structural failures, we know that the earthquake imposes sudden dynamic loads on buildings, which often lead to the various structural and non-structural failures. Unlike the static loads, seismic forces will cause the repeated cyclic loading under tension, compression, shear, so which many conventional structures are not designed to withstand. Failures during earthquakes generally occur due to weak connections, poor material quality, irregular design, or lack of seismic detailing. So while recognizing these typical failures is essential for improving the seismic resilience and preventing the loss of life and property. So some of the common structural failures are soft story collapse, short column effect, overturning of slender walls and chimneys, the diagonal shear cracking, the pounding between the adjacent buildings. The root cause of these damages can be traced to the both design and the construction deficiencies. The lack of compliance with the seismic codes, the poor detailing reinforcement, the ignoring the ductility. So these will make the structures highly vulnerable to earthquakes. Material issues such as the weak mortar in masonry, the poor quality concrete, it definitely will reduce the strength. Then the inadequate connections between the structural elements such as between the roof wall, the beam column, they will lead to the separation of these members and it will eventually to collapse. Additionally, the non-structural components like infill walls, the facades can worsen the situation by falling off or imposing unexpected forces. In addition to the structural failures, some non-structural failures also will be susceptible to damage. That is the partition walls, the glass panels, suspended ceiling, the mechanical or electrical equipment, they will often fail due to the excessive storage drift. So the lifeline structures that are considered as bridges, water tanks, the pipelines, may also suffer damage, disrupting the essential services. So while understanding these causes of typical failures, so that will helps us to formulate the preventive measures. So we should ensure the buildings with regular geometry to avoid the weak story designs to adhere strictly to the seismic codes are very essential steps. By providing the ductile detailing, confinement reinforcement and continuous load transfer path, they will significantly improve the seismic performance. While retrofitting the existing vulnerable buildings with the shear walls, bracings or jacketing can also reduce the risk of failure. Ultimately, earthquake resistant design is about anticipating these failure modes and incorporating redundancy, ductility and energy dissipation mechanisms into the structures. So when coming to the lessons learned from past earthquakes, the importance of learning from past earthquakes is, so every major earthquake provides valuable insights into how structures behave under strong ground motion. Failures and collapse will reveal the weaknesses in design, in the materials, in the construction practices, while surviving buildings highlights the effectiveness of good engineering design. So while learning from past earthquakes, it is therefore crucial to improve the seismic codes that develops the resilient structural systems that will ensure the future disasters result in less damage and fewer casualties. The past earthquakes have repeatedly shown that the building configuration plays a vital role in seismic performance. It highlights the importance of adapting regular, symmetrical and balanced design. One of the most important key takeaways from earthquake damage studies is the role of the choosing of materials and the detailing. The poor quality concrete, the weak mortar masonry, and inadequate reinforcement will be a major contribution to the collapse. Conversely, structures with the ductile detailing such as the confinement reinforcement, strong beam column joint, and the seismic bands in masonry, this will show far superior performance. This ensuring quality control in construction and ductile detailing. Another critical lesson is that the existing vulnerable buildings that poses a significant risk during earthquakes. Many collapses occur in older, non-engineered or non-ductile structures that were built before the seismic codes were enforced. So retrofitting techniques for such kind of buildings such as jacketing, adding shear walls, the using of base isolators. So this will significantly reduce the vulnerability of the structure. Equally important is the community preparedness, including the regular earthquake drill, awareness program, the proper emergency response system. So this will majorly reduce the casualties even when the structural failures occur. The ultimate lesson from the past earthquakes is the need to build a culture of resilience. This involves not only updating seismic codes and engineering practices, but also enforcing building regulations, training professionals, and educating the public. Disasters like Bhuj, Nepal, Turkey, Syria have shown that preventable structural failures cause the majority of casualties. By applying lessons learned, strong design, quality construction, retrofitting, and the preparedness, the societies can transform earthquake from catastrophic events into manageable national hazards. Thank you.